Hi all. In this lecture, we will set up and provide solutions to the problem of learning Markov decision processes with low regret. Okay, so in order to do this, let's first recall what we've seen about learning finite horizon and finite state action Markov decision processes. So if the state transition probabilities and the reward function are both given to the learner, then learning the optimal policy without with this knowledge of T and R. T is the transition probability table and R is the reward function for a finite state action Markov decision process can be done by what is called the perfect Q learning algorithm, and this is basically a form of dynamic programming, backward dynamic programming or backward induction, where you basically start by initializing the optimal Q value function to be 0 right at the end of the horizon, and in every other step you um, you basically back propagate the existing values at the optimal Q values at stage h plus 1 back to stage h, and that is how you get the you can solve for the optimal Q values as well as the policy, the optimal policy along the way. Okay, so this is when there is no learning required. This is in some sense a planning or an optimal control problem. In the case where the learner is not provided explicit information about T and R, about the dynamics of the MDPT as well as the reward or utility function R, uh, we saw that when instead of providing the complete T and R, the learner is provided with simulator access to T and R, in the sense that there is an oracle or a black box or a generative model that when given any input as a state action pair SA gives a typical sample from the reward distribution corresponding to that state action pair and the next state distribution corresponding to that state action pair. So, if there is a simulator like this available, then we have we define what is called the Q learning algorithm for the finite horizon H MDP problem, which basically initializes an arbitrary Q value function as a proxy for the optimal Q value function, and thereafter what it does is it repeatedly selects a tuple consisting of a time step within the time horizon small h, a candidate state S and a candidate action A, and implements the following recursive update, which is that it updates the proxy for the optimal Q value function at stage small h of the MDP of total horizon capital H at the state action pair SA with its previous value plus a small correction, where the correction is basically equal to the difference between the reward at that state action pair plus the best possible downstream Q value estimate of that state from that state action pair minus the original value for the optimal Q value for H at SA. Okay, so this is basically Q learning for finite horizon, and we saw that with some conditions. So with some conditions on how this H, S, and A are selected, it converges in fact to learning the optimal Q star value function. If for instance states, actions, and time steps H are explored sufficiently enough. So that was a typical condition that was required to show the convergence for Q learning, as we talked about in the previous lecture. So what we are going to do today is take the learning problem one step further and insist on what is called low regret learning, uh, in the sense that the balance between exploration across states actions and exploitation of learned knowledge to actually do well in the sense of taking actions is required to be balanced in order to get low regret. So, we will define formally the concept of regret in an MDP, and for that we will find it useful to define what is called an episodic model of learning, finite horizon MDPs. So, the motivation for an episodic model of learning as opposed to a generative model of learning or a simulator access kind of model of learning, which is what we have here, okay, where one can query arbitrary state action pairs to the simulator at any time, is that in many applications we may not really have the luxury of actually having simulator access to learning what happens when you take an action A at a state S. So, imagine a physical system like a robot or a robotic arm, or even a car, let us say an autonomous car, a self-driving car that you are learning to control. So, a physical system is often uh, represented at any point in time by a state that contains, for instance, its location, its position, its velocity, its acceleration and other dynamical features. And it is not often feasible in real life settings to actually place such a system in the exact configuration of a given state S and then experiment and see what happens when you play a certain action. So, it may not be possible to easily uh, force the system to get into a certain state. On the other hand, the episodic learning protocol is something that is more suited for that. And so, what is this episodic learning protocol? Well, it is the following. So, the goal is as usual to solve a finite horizon MDP or to find its optimal policy. So, at each episode, so there are learning epochs called episodes within this episodic learning protocol. At each episode indexed by, let us say, k, what happens is that the environment or the MDP sets the start state to be drawn from the probability distribution rho of the MDP. So, SK1 is notation for the first state of the MDP in episode k. This is drawn according to the MDP's intrinsic initial state distribution. Okay, so informally, the MDP resets its starting state, followed by this at each round within the episode or time step within this episode, where time steps range from within the finite horizon 1 through h. The learner now has a chance to experiment. The learner gets to observe the current state SKH. So, recall that h is equal to 1 initially. So, the first start state is observed. Followed by this, the learner can play an action denoted by AKH from the action space. And by the way, this can be based on all the information obtained by the learner so far, all past information seen by the learner so far. After this, the MDP transitions in state. So, SKH plus 1 is drawn from the unknown state transition distribution of what happens when you play action AKH at state SKH. Okay, so, imagine that the MDP advances the state or the system responds to the action AKH being played by the learner, and consequently the learner also gets or observes a reward RKH drawn from R, the reward distribution at state SKH, and in response to action AKH is observed by the learner. Okay. So, this is the basic structure of an episodic learning protocol. So, after h steps have been executed within an episode, then it is time for the environment or the dynamical system or the MDP to reset itself. And so, the next state, the first state of the following episode is automatically going to be drawn independent of everything in the past from the state distribution rho, and then the learning process carries on as usual. So, here is a pictorial description of the episodic learning framework. So here the horizontal axis is time steps or rounds, and this is the first episode. Okay, so within this are H time steps. At the end of this first episode, the state resets itself, and then the second episode begins. Then the state resets itself. Then the third episode begins, within which the learner is allowed to play or experiment with different actions or change its policy from the past in any causal way possible, depending on the past. Okay, so the state resets occur at once every H times, capital H time steps. Okay, and one comment that is worth making here is that this episodic learning framework, in some sense, is more difficult or more challenging than learning with a simulator or a generative model. Uh, Basically, because of the reason that in episodic learning, the learner cannot really control the state evolution part of what happens when an action is played at a certain state. Recall that in episodic learning, the environment or the dynamics naturally give rise to the next state of the MDP, at which the learner is called upon to make a new action, as opposed to the generative model or the simulator based learning model, where the learner has the freedom to set the state of the system at any state of its any state that it wishes to experiment with, and play any action A. Okay, so there is a hard reset kind of ability allowed in the generative model setting, which makes the episodic learning setting a little more challenging and restrictive. Okay, so you cannot control the state evolution part, and you have to be content with what observations you get by playing actions at certain states that have already evolved. Okay. So the next important thing, once we have defined this episodic learning setup, is to define the notion of an algorithm with low regret. Okay, so um, the regret of the learner in an episodic learning model is basically so informally it is the shortfall in total reward suffered by not playing the best policy in each episode. So one formal way to define this is to say that the regret after k episodes, okay, so k here is going to mean the number of episodes, the total number of episodes for which the learner has interacted with the unknown MDP and tried to learn something about its optimal policy. So you sum across all episodes, so this is a notion of cumulative regret, the expected value of, so what is this? So we want to take the sum of all the rewards that were actually obtained by the learner in episode K, that is just the sum, so let's recall, yeah, RKH, RKH. So this is the total, this sum is the total amount of reward that the learner made in episode K. What is the best possible expected reward the learner could have made in the same episode? It's by definition V1 star at state SK1. This is the best possible total value in capital H time steps that any policy could make starting from the initial state SK1. Okay, and we also implicitly assume that the expectation is over the distribution of SK1 as well, which is the distribution, the probability distribution rho on the state space. Okay, so just to be clear, this expectation is over the randomness of the learner's action choices and the MDP's state transitions, states and rewards. Okay, so the learner's responsibility is to generate an action at a given state within an episode, and the MDP in response generates the next state and the a corresponding reward. Okay. So the regret. So this is the regret of the learner, and in some sense, the problem of low regret or online learning in MDPs is the problem of how to build efficient learning algorithms that can keep this regret low over time. Okay. So here's a first candidate approach. The naive approach, based on what we've seen so far, would basically say, since we don't have knowledge of the MDP upfront, we could just use Q-learning with some uniform exploration thrown in that basically helps to learn the optimal Q value functions better and better over time. And once you have gotten close enough to the optimal, to learning the optimal Q value functions, Q star, then you would probably not be deviating too much from playing the optimal policy that gives rise to V1 star, okay, in each episode. So more precisely, what this approach suggests is that at each episode, so this is the same, this is a recap of the same protocol here, the episodic learning protocol that we presented here, except with some details filled in. Okay, so the details filled in here are that the only details we need to fill in are how to play the action as dictated by the learner. Okay, and here the naive approach essentially says just play a random action AKH. So at any time within any episode, just play a uniformly random action. Okay, and you could just respond on the MDP responding to this random action with the next state and the next reward. What you could do is you could just use the observation of the next state and the reward to perform the usual Q value update. Okay, so this is just Q learning again. Okay, which is the following update here in red. Just saying that apply Q learning with completely uniform and completely random exploration. So just play a random action and then update these Q tables, the optimal estimates for the optimal Q value function as you go along. Okay, so irrespective of the fact that you're not allowed to change the state of the MDP from the learner's side, you can still play a random action each time and then continue updating your Q value, the optimal Q value estimates, just as you were pretending to behave in the generative model or simulator access kind of setting. Okay. So even though the key thing to note here is that even though this could converge, even though your optimal Q values could actually converge to Q stars, you're not really doing anything in the sense of playing the optimal policy. So you will still be essentially playing only random actions in spite of your estimates of Q star, the estimates Q tilde H converging to Q star. So this basically says that this is a very naive form of exploration which adds constant regret. Okay, this is just adding constant regret because you're not really adapting from the results of your experience to change your policy over time. So this adds constant regret per episode, which leads to basically linear regret with the number of episodes, the total number of episodes. Okay, so one way to fix this could be that one could play a random action. So you could basically do epsilon greedy, which is that you play a random action with probability epsilon and the optimal action suggested by or for the current Q value estimates Q tilde with probability 1 minus epsilon, but this will still give you a linear regret because of the linear the constant rate at which you are playing random actions. So with probability epsilon, certainly you are not playing you may not play the optimal policy in each round, and that will lead to a linearly growing regret with each time. Okay, so the main question that presents itself at this point is how can we slightly do better exploration instead of this very naive exploration across actions to try to keep your regret small. Okay, so you should explore state action pairs for which you're not very certain much more often and you should stop exploring a lot if you are confident about the Q value of a certain state action pair. So that's sort of what that's the question that this simple exercise poses, and that is addressed, that can be addressed by several approaches. Here we will present this approach, which is called Q learning, with what are called UCB bounds, upper confidence bounds. This is also called Q learning with UCB exploration. So think of this as essentially um, a smarter way to explore uh, within the MDP. And precisely this can be done by maintaining what is called an optimistic estimate, or in other words, a statistically plausible bound for Q star HSA, the optimal value from playing action A at state S in time step small h at all times. Okay. And once you can build a statistically plausible upper bound on Q star HSA, one could just play sort of the greedy action suggested by Q star H at every state within the episode, and hope that this leads to only as much exploration as is required. Okay, so the details of this algorithm which we are going to present can be found in this paper called Is Q Learning Provably Efficient by Jin et al. And this appeared at NeurIPS in 2018. Okay, so to state the algorithm or the exploration strategy for Q learning more specifically, we'll start by making the assumption that that all rewards are bounded for ease of presentation and analysis. So for all states and actions in your discrete state action space, reward distributions are between 0 and 1. And here's the algorithm which we call, which the authors called Q learning with UCB Hofding. The name UCB Hofding is because this algorithm uses Hofding's inequality to get statistically plausible upper bounds for the optimal Q value functions. There are more sophisticated concentration inequalities like Bernstein that one could use, which are also presented in the same paper. So this is the algorithm, the Q learning with UCB algorithm, and it starts off by initializing a Q value table as usual in the spirit of the standard Q learning algorithm. So we'll call these this table of optimistic Q values Q upper bar, Q bar H S A. So think of these as basically plausible upper bounds with high probability for the Q star values at any time during the learning process. So you initialize this to the largest possible uh, total reward in h time steps, and since we are assuming that every reward at each time step is bounded by 1, the largest possible uh, reasonable upper bound for Q for the entire reward within an episode is simply capital H. Okay. So this is like a default UCB for Q tilde for Q star as an initialization. You also initialize play counts of every state action pair corresponding to every step in the episode in the finite horizon to 0, and you also initialize UCBs, upper confidence bounds, for the optimal value functions, which are just a function of the start state again to H, and this is for all H, S and A. Okay. So NHSA is going to keep track of the number of times that the learner plays SA at H. Okay. The input here, we assume also that the algorithm takes as input a confidence parameter which following our standard convention we will call delta. So this delta is basically an error probability parameter. And what the algorithm does is basically the following at every episode. So recall that it's operating in the episodic learning loop. So at every episode k, uh, you first get the start state, the reset start state according to row, and then for every round or decision step h in 1 through h, what the learner does, so the learner, it's time for the learner to play an action. So the learner plays the action akh, which is just the usual greedy action, assuming that the current table of q values was the actual table of optimal q values. So this would just be mimicking an optimal policy, but with the currently available set of q values. So q bar h corresponding to the given state skh and maximizing over all possible actions a prime. Okay. So if q bar were actually equal to q star, then this would actually be playing the optimal policy, but there could be some uncertainty in q bar relative to q star. Following this, the learner naturally receives the next state. After this comes the um, so we'll also assume, so by the way, we will also assume in this analysis, in this description, that R is known. So the only uncertainty in this development is the uncertainty in the MDP's dynamics or the state transition matrix T. This is actually without any loss of generality, as there is existing work in reinforcement learning that shows that the hardness of reinforcement learning is primarily due to the lack of certainty in knowing the transition probabilities as opposed to the uncertainty in knowing rewards. And it's quite clear by now that the MDP learning problem is the source of hardness in MDP learning is because of learning T as opposed to learning R. Okay. So we'll assume that R is known. If R is not known, again, it can be easily extended to cases where R is not known, but that's not going to affect the complexity of the result. So set T to be, so T is defined as NH SKH AKH. This is just the notation for the number of times that state action pair SKH AKH was visited. And so this is just set to be NH. So update this state action pair play count by 1 because you just played action AKH at state SKH. Plus 1. And we will set BT as something that scales roughly as 1 over square root of the number of number of plays of the state action pair SKH AKH. More precisely, this is some constant times square root of h cube divided by T log SAKH by delta. So this is where the Hofting type concentration bound confidence radius comes in. And then the final step is to update Q values. Q value upper confidence bounds as follows. Q bar H at SKH AKH. So this is just the usual Q value update plus an addition of confidence bound. So it's as usual 1 minus a step size into the existing value plus alpha times the update plus V bar H plus 1 Sk H plus 1, except that there is the addition of this optimism bonus, okay, this optimism or uncertainty bonus Bt added here. So this is the same Bt that essentially adds about 1 over square root number of times SA was encountered. Okay. So this is the exactly the same as the Q-learning update, except that you add this artificial bias Bt here that that is equivalent to a bonus for exploration for an underexplored state action pair, and followed by this you just update your value function estimates to stay consistent. So V bar H at SKH is by definition, I mean this is intuitively the largest possible Q value that you could get at any overall possible actions at SKH, except that you take the min of this with H, because we also know that no value function can actually exceed H, because all rewards are bounded by H per stage. Okay, so this is naturally truncating optimistic value function estimates beyond capital H to capital H. Okay, one last thing to specify is the step size alpha t. So alpha t is essentially decaying as 1 over t. Okay, so this is basically 1 over t. T, recall T is the play count of the state action pair that is currently being played. Okay, so this is the Q-learning algorithm. It essentially adds this penalty for under exploration of states and actions, hopefully with a view to avoiding explicit exploration across states and actions and exploring only to the extent required. Okay, and the fact that the exploration is just about enough to actually keep the regret small is stated in the following theorem. So let me state the theorem here that Jin et al. Proved for this Q-learning algorithm with UCBs. So theorem, and this is basically a regret bound for Q-learning with UCB. Okay, so what it says is that for any given delta in 0, 1, if this algorithm above is run, then with probability at least 1 minus delta Q-learning with Hofting, Q-learning with UCB Hofting gets in k episodes a regret of order, so h raised to 4 SAT log SAT over delta inside the square root in k episodes of learning. Okay, so the key thing, the key takeaway here is that this is order square root uh, k, so square root t, and since t is equal, so t is equal to kh, t is the total number of time steps or decision rounds elapsed in k episodes, which is naturally the number of episodes k into the number of time steps per episode small h, and this is order square root t, which is order square root k. Okay, so the total cumulative regret of Q-learning with UCB Hofting scales only sublinearly in the number of episodes taken to learn. Okay, which is why it's an indication of the fact that the algorithm is not exploring more often than required. Okay, and more precisely, if you convert this in terms of the number of episodes, this is basically square root. So up to log factors, which is why we put a tilde here. This is h raised to 5 SAK. Okay, regret. So the attractiveness of this algorithm is really that it doesn't really, it's a model-free algorithm, just like Q-learning is, in the sense that it doesn't explicitly learn the probability transition matrix T or the structure of the dynamical model T for the MDP. Rather, it just updates Q values by following the principle of dynamic programming, but for this extra exploration bonus. And so its memory and space requirements per iteration are very low, and it still manages to explore to the extent of keeping regret fairly low. Okay. The last approach that I want to present is an alternative approach to obtaining low regret algorithms for MDPs, and this is along the lines of what is called model based RL. Okay, so recall what a model based algorithm does. The model based approach consists of actually trying to first learn the T and the R functions. So in our case, more specifically, the transition probability function of the unknown MDP and the reward generating distribution explicitly. Let's say up to a certain level of accuracy specified by confidence sets. And then once we have estimates, good enough estimates for T and R, then one could perhaps try to just directly estimate the optimal policy for that proxy for the real TNR. Okay, so that is what model based reinforcement learning proposes. You essentially learn the entire model or equivalently the transition probability table for the MDP. Okay. So the idea here is to first estimate T and R up to confidence sets, and then estimate, then proceed to estimate UCBs for Q star H using all the statistically plausible T and the R functions that you've learned, and then just play naturally with respect to these Q value UCBs. So finally, we ultimately do build upper confidence bounds for the Q values, but this is done implicitly by first building a entire family of plausible T and R functions depending on the data that has been seen, and then generating upper confidence bounds for the Q stars, which will be used to play in a greedy way. Okay, just like the optimal policy would do. And so this an example of this strategy for finite horizon MDPs is given by this UCRL2 GP algorithm, where UCRL stands for upper confidence reinforcement learning and GP stands for greedy policies. So this was a paper by Efroni et al. At NeurIPS in 2019. So what does this algorithm do? How does it build upper confidence bounds for Q values? Uh, uh, just like the previous algorithm did, but in an implicit way depending on the model. Well, here is how it does it. It first initializes upper bounds for Q values, which is again Q hat H S A. So we'll call them the same Q hat H S A, and it initializes them to the largest possible default values, that is capital H. NH SA are initialized again to 0. V hat H of S, the optimal value function estimates are initialized to H, are initialized to something like H for all S, A and H. So what it does here is that at each episode, after the initial state is drawn by the MDP, and the episode starts. So at each round of the episode, indexed by small h, what it does is it loops over all actions and it constructs an upper bound for the optimal Q value function at that stage, at that current state, and the candidate action A by using a subroutine called optimistic Q as a function of r hat, t hat. N is essentially a table. Recall that N stores the state action play counts so far played by the learner. Think of r hat and t hat as basically point estimates for the reward function and the transition probability table, along with the number of times each state action pair has been sampled in the past and your current v hat h plus 1, the optimal value function table. And this is a subroutine that I should mention uses upper confidence bound ideas. So this is where the UCB ideas come in. So this subroutine is responsible for translating estimates of the model, which is essentially t hat and r hat, into optimistic estimates for derived functions of the model, which are basically the Q values. And after this, you play the action AKH as usual in the greedy fashion with respect to the plausible upper confidence bounds on Q star that we currently have. Okay, after this, the optimal value function estimates are updated to be the min between the previous estimate and the new Q value estimate returned by the best possible action at SKH. After this, you get the next state. SKH plus 1, sorry. Right, so you set right, and using this you can basically update. We break out of this inner for loop, and then outside when you break out, you update your estimates. So since you've got one new state transition, information for one new state transition, you update your estimates r hat and t hat with the in fact what happens is that this policy stays fixed for this episode. Okay, so as long as this episode lasts, the same Q hat. So what determines the action is the Q hat during an episode, and this never changes during the episode. But however, when the episode ends, all the data from this episode is used to update your estimates for R and T. Okay, so update R and T with the trajectory that is SK1, AK1, RK1, SK2, and so on, all the way up to SH1, SKH, which is what happens at the end of the trajectory. So this is the trajectory during the episode, during the kth episode. Okay, and this is broadly a step that we will refer to as model estimation. The other important step is called optimistic Q star value estimation. Okay, which is performed by the subroutine optimistic Q. So we won't detail the subroutines, this optimistic Q subroutine, as well as the model estimation subroutine in this lecture, but we will just end by stating the following result, which is a regret bound that was derived by the authors of this paper for the UCRL2 GP algorithm. And so this is a regret bound for UCRL2GP by Efroni et al. This regret bound states that when the learner applies this algorithm for any number of episodes k with probability at least 1 minus delta, the regret of UCRL2GP is order so well this is O tilde up to log factors HS square root A T. So we'll always use the convention that T is equal to KH, the total number of time steps elapsed in the learning process, plus H square. So this is something that does not scale with the number of episodes. H square root S into SA. Okay, so if you want to look at this primarily from the point of view of scaling with respect to the number of learning episodes taken, then this becomes HS square root AKH, which is equivalently h to the 3 by 2 S root AK. So if we compare, so this is a model based approach in the sense that it essentially uses information, it learns the model implicitly along the way. The T hat is testament to that. And if you want to compare this with the model free approach regret, the dependence on H, so this was h to the 5, so that's h to the 5 by 2 square root SAK, right. So here the dependence is much better in terms of the time horizon, but it is somewhat worse in terms of the dependence on S. Okay. So in general, this is sort of the so this algorithm uses more information than the model free Q learning algorithm of Jin et al. In the sense that it also estimates the model, and that leads to a reduction in the dependence on capital H, although in this particular result there is a worsening depending on the size of the state space. So this concludes this lecture. We will unfortunately not have the time to give proofs of these regret bounds for both UCRL2GP and the UCB Q learning algorithm. But I urge you to read these pieces of literature if you want a detailed description of the derivations there. Thank you again.